Alrighty, let's continue our discussion of concentration. This time we're going to specifically talk about solution dilution. So this is when a chemist, or people use this technique in other industries as well, you take something that's super concentrated and you add water usually, and then you change it into something that's less concentrated, less strong. The formula here is M1V1 equals M2V2. So M stands for molarity, and the V stands for volume. It doesn't matter who you plug in for M1V1 as long as you're plugging in matched sets. And we'll talk about that a little bit more when we get into the problem. So this part is flexible. Who's M2V2? Well, as long as they go together, they can be whoever you want in the problem. The other big thing is that the units of volume are super flexible, but they must match. Here, when we did molarity equals moles or liters last week, I said the units are super strict, right? So we had to use liters in the denominator. There's no way around that if you're using this formula. However, here we can use milliliters, we can use liters, you can use microliters, any units of volume that you want, as long as they're the same on both sides, and then they'll cancel out for us. A couple things I like to discuss with the class before we jump into the actual problems are some of the motivations for diluting solutions and approaching solution prep this way, and some examples from our day-to-day life. So I always ask people to think about, what are some concentrated solutions that you have physically diluted down? One of the main examples that people will mention is frozen juice. So if you've ever purchased like frozen orange juice, or I don't know, frozen lemonade or anything like that, you know, it's very small, and then you add a bunch of water. And so we want to talk about the motivation for this approach. So when you buy frozen orange juice, concentrated juice, you're usually doing that to save money. And sometimes, right, it's an issue of space, right? If you don't have space in your refrigerator for a big jug of juice, well, you can get that little container of the concentrated stuff and put it in the freezer for a bit until you're ready to prep and drink that juice. There's other examples too. I remember I worked in restaurants in the beginning half of my life. I worked at McDonald's and I worked at a couple other restaurants. And I remember every time we had to clean something, there was little packets of concentrated cleaners. So for instance, when you mop the floor, you grabbed one of these little packets and it said, then fill the bucket with hot water. So we weren't using the little packets straight, right? You're going to dilute them down. So we do encounter a lot of concentrated cleaners in our life. Those are very common. Students come up with such creative examples when this is a hall class discussion. In chemistry lab, we typically use solution dilution to prep our acids and our bases. So there's a couple reasons for that. Besides saving money and saving space, what we do is we'll get like sulfuric acid, hydrochloric acid. Those are liquids when they're pure. So it's not like a lot of the other stuff we're using, they start as solids. And so we just have a bunch of solids sitting and we prep them the way we discussed last week, where we do the grams to moles and we do that. However, with acids and bases, they're typically liquids. So we buy them as concentrated as they'll sell them to us. And so we have these jugs of very, very concentrated acids and bases in the back, in the stockroom. That gives us maximum flexibility. So a Chem 100 lab might need 0.1 molar hydrochloric acid. but then, I don't know, CHEM 110 needs 6 molar. So because we have it super, super concentrated, we can manipulate that one bottle, prep, you know, liters and liters and liters upon liters of solution to any concentration that we want. So flexibility is key for us, apart from the other reasons that you're already familiar with from using concentrated things at home or at work. And then the last thing that I'll just briefly mention is it is better for the environment overall. Even stuff like the frozen juice, right? Maybe you have a pitcher at home that you can wash and reuse. So instead of throwing out a huge plastic jug every time you drink some orange juice, now you're just throwing out that little cardboard container. So using concentrated cleaners and consumer products and chemicals results in overall less waste. So very common scenario here. Someone needs 1 liter of 0.646 molar, but they have the more concentrated 2 molar hydrochloric acid on hand. So when I go through problems like this, I like to label things. So I would call my 1 liter V1. I know it's volume because it has units of liters. And then here I have an M, and it goes with the 1 liter. That's a set. So I'll keep them both with a subscript of 1. And then starting with 2 molar, so this could be my M2 value. So what I'm missing here is the second volume. How much of the concentrated stuff do I need to put? So we're going to use M1V1, M1V1 equals M2V2. So I have 0.646 molar times 1.00 liters equals 2.00 molar times V2. I don't know what V2 is. Let's put it in different colors so it stands out. That's our unknown, that's our variable. So I want to isolate this. So I'm going to multiply these two values. I'll just put parentheses because we can do it all in one step in our calculator. And then I'm going to divide each side by 2.00 molar. When I do that, I got V2 equals 0.323 liters. Always check how the units are canceling out. So we have, this goes away completely, right? And then molarity cancels with molarity, and we're just left with liters. I never use liters in the lab. Most of the time, our glassware that we have available has milliliter increments. And if you're working in a biochemistry lab, microliters is even more common. So I'm gonna change this. I know the problem didn't tell me to do that, but they want a description. So I want a description that fits what, you know, is realistic here. So I'm gonna change this to milliliters. So I'll do 1 liter has 1,000 milliliters. And so we're looking at 323 milliliters. Now, that's not the final answer because they want a description. This is V2. So this matches with the 2.00 molar. So I'm gonna measure out (323 milliliters of 2.00 molar hydrochloric acid. What do I do next? Well, we want to make it less concentrated. We want it to go down to 0.646 molar, and we want to make 1 liter of it. So we're going to have to add water to get this value up to the 1 liter. 1 liter is 1,000 milliliters. So I'll do 1,000 milliliters minus 323 milliliters. trying to do this in my head. What is that? 677? Yes. So 677 milliliters of water. So our concentrated stuff plus the water should equal our target volume. So measure out this much of the hydrochloric acid, then add 677 milliliters of DI water. How would you prepare 60 mils? So I'll call this V1 of 0.200 molar. That's a matched set, so I'll keep it together. Nitric acid from a stock solution of 4.00 molar. So I'll call this my M2, and that means that I want, or I'm solving for V2, the volume of the stock solution that I need to use to prep this new solution. So once again, we'll use M1V1 equals M2V2. And we'll plug and chug into the formula. So 0.200 molar times 60.0 mils. It's okay to use the milliliters. We'll just get milliliters on the other side. Equals 4.00 molar times my unknown, my V2. So I need to isolate V2. So I'm going to put parentheses around this. And I'm going to divide each side by 4.00 molar. When I did that, I got a value of 3. And I also want to just pay attention to my units. So the molar would cancel, so then I'm left with units of mils, which is fine. I like mils, that's what we use in the lab, right? So I got V2 equals 3.00 mils. This volume matches M2. So when I'm actually prepping this solution, it says, how would you prepare it? I need to grab 3 mils of 4.00 molar nitric acid. Then as a chemist, you need to know, how much water do I need to add? Well, we're trying to prep 60 mils altogether. That's what we want our final volume to be. So I'm going to do 60 minus the 3, and the rest of that's going to be water. So 60.0 minus 3.00. So I'm looking at 57 mils of water to get to volume. And of course, if you're doing this, you want this to be DI water. The description, right? I kind of ended it right there. Of course, you're going to mix these thoroughly. So a glass jar of acid, it contains 12.5 mils. I'll call that my V1. Of 12 molar, that's going to be M1, hydrochloric acid. The total volume is brought up to 200 milliliters. So my V2, at the end of the day, there's 200 milliliters altogether in that bottle when they added the water. What is the new concentration of the acid in the bottle? So I can do M1V1 equals M2V2 here. My first molarity is 12.0 molar. And then I have 12.5 mils. I don't know M2. However, I do know that that second volume is 200 milliliters. I'll put some parentheses here. This is how I'm going to plug it into my calculator. And then I'm going to divide by 200 mils. Milliliters cancel milliliters, and so we're just left with units of molarity. So M2 then, there's 3 sig figs as well, so I'm going to report this as 0.750 molar. Alrighty, same approach. We're looking for the final concentration. Alrighty, same approach. We're looking for the final concentration. Can't talk tonight. Alrighty, same approach. This time we're looking for the final concentration. So right away I know that I'm going to call it M2. So 75 mils of a 3.50 molar glucose solution. So we have a V1 and M1 right here. And then they gave us V2. So somebody diluted that to 400 milliliters. We have milliliters on both of our volumes, so we're good to go there. I'm going to do 3.50 molar times 75 mils equals M2, which I don't know, times 400 mils. I'm going to divide each side by 400 mils because I'm trying to isolate M2. Just as a reminder, once again, if you're trying to plug this in all in one step in your calculator, you need parentheses around that numerator, or else you might not get the right result there. Alrighty, so when I plug this in, I got a molarity of 0.65625. We can look at the sig figs real quick. Even though that volume, that V2 has 4 sig figs, the other values only have 3 sig figs. So I'm actually going to report my final answer as 0.656 molar. And a follow-up question, just because I know it's been a point of maybe a little bit of confusion in the past. So in those earlier problems, we talked about how could you prep this solution. So the question that I want to ask you all is, how much water did they use? So they added 75 mils of the concentrated stuff, and then at the end of the day, they had 400 mils. So the difference in those volumes will tell me how much water they added. So I know they added 325 mils of DI water. So in this problem, we're asked to solve for the concentration, the final concentration of a solution that's been diluted. So right off the bat, I know what I want. I want to solve for, I'm going to say M2. They gave me a V1 and an M1. Those go together. And then over here, the 400 mils represents my V2. I'm going to use the M1 V1, M2 V2. And plug in everything into that. So 3.50 molar times 75 mils. M2, I don't know. And we have 400 mils. I'm trying to isolate M2, so I'm going to divide each side by 400 mils. That cancels. The milliliters on this side will cancel, and I'm left with molarity, which is perfect because I'm trying to solve for M2. Again, just as a quick reminder, when you plug this in your calculator, you need parentheses around this top here, around the numerator. Numerator. So 0.65625. Looking back, we only have 3 sig figs. So I'm going to report my final answer as 0.656 molar. As a quick follow-up question, we know that someone took 75 mils of 3.50 molar glucose in order to make this final solution. How much water did they add when they were making this solution? So again, the approach of that is we know our final volume, which is 400 mils, and we know they added 75 mils of the stock solution. So the difference between the final volume and the concentrated stuff will tell us how much water they added. So it looks like they added 325 mils of DI water. So I just wanted to show you all volumetric flask. This is a piece of precision glassware. So you may notice that it says 250 milliliters on this particular volumetric flask. So they only come in particular sizes. They have really, really small ones that are about 10 mils, and you can get 100 mils, 250, so on and so forth, 2 liter, 1 liter, but you can't get them at random volumes. The reason why is it's quality glassware, high precision, better than a graduated cylinder. Somebody did QC on this quality control and ensured that it was going to be exactly 250.0 milliliters. As long as you fill it with solution, there's a little line right there. So if you're filling it with solution, you want the bottom of the meniscus to be right on that line, right at the top of that line. And the way you would use this is you'd put the stock solution in first, and then your final volume, if you're using this one, should be 250 mils, and then you fill it with DI water. And then there's this ground glass stopper. And then inside here is also ground glass. And they actually seal together perfectly. So that last step, when you have to stir or mix, you can actually just flip this upside down and you don't have to worry about it leaking or anything. So I just wanted to show that to you. You do get to use them in some of the more advanced courses. It's just that they're very costly. Something like that would probably cost between $30 and $40. So V1 right here, M1, and they gave us an M2. The problem asks us for specifics about preparing this solution. So I'm going to use the Alt standby. And I'll do 0.125 molar times 505 milliliters equals M2, we don't know. Or no, we do know M2, we don't know V2. And that's why I always like to label that stuff ahead of time. Keep everything straight. Alrighty, so the step is the same. I'm going to divide to isolate my unknown. So I'm going to divide each side by 0.100 molar. The molarity cancels, and I'm left with units of mils. So V2 here is 631.25 mils. Quite a strange answer. And the problem asks us about how we're going to accomplish this task. So what's going on? You're starting at 505 milliliters and your final volume is 631.25 milliliters. Why such a small change? Well, we're not trying to change the concentration here all that much. We're just trying to tweak it a little bit. It's currently at 0.125 molar, and we need to bring it down just a tiny bit. And so it seems like we're just going to need to add about 100 mils of water. Let's do that and get a precise number so we know how much water exactly. So our final volume is 631.25 mils. And we started with 505 mils. So we'll subtract those two numbers. And we get 126.25 mils. And this is going to be water. So let's write a step-by-step procedure for accomplishing this task. So I just talked about the volumetric flask. I wouldn't use a volumetric flask here because this final volume is a little bit random. The volumetric flasks come in more predictable volumes, like 100 mils, 250 mils. We use the 1 liter volumetric flasks all the time. But you're not going to find a volumetric flask for this volume here. So, and these are quite large volumes, so I would lean towards using a very large graduated cylinder. That's going to be our best bet. Graduated cylinders are pretty good. A volumetric flask would be a little bit better, or a pipetter, but I'll take a graduated cylinder for something like this. So I'm going to measure the 505 milliliters just to kind of confirm that I actually have 505 milliliters using a graduated cylinder. At this point, I would probably pour it into a large beaker because I'm going to need that big graduated cylinder for my next step. So maybe like a 1 liter beaker or something like that. To be honest, the size of the beaker doesn't matter all that much as long as it's large enough to hold all of the volume. Then we need to add 126.25 milliliters of DI water. I actually want to use this same graduated cylinder that I just used because it kind of serves as a rinse step, just in case a little bit of that hydrochloric acid got left behind, a couple of drops or something. Adding that water would help grab it. So I'm gonna measure. I'm not going to be able to measure and you'll gain this familiarity with the different types of glassware the more you work in the lab. But the graduated cylinder isn't going to give us the 0.25 part. We don't have that level of precision. But I'll do 126 mils. Of my DI water with the same graduated cylinder. And then we'll pour into the beaker with the other stuff. And stir it. You could use a stir bar or a glass stirring rod to mix that up. But we want to make sure that we're creating a homogeneous solution.